Today we are going to have a quick recap of environmental science net UGC net material. A really quick one. If you are running out of time, just watch this. After completing all the material, then we will be having a quick recap like this. So you need to learn all the material from standard books, and then we will be having a quick recap. Environmental science is an interdisciplinary field that examines the complex relationships between the natural environment and human activities. It encompasses a wide range of topics including ecology, environmental chemistry, geology, climatology, and social science. First, ecology is the study of how organisms interact with their environment. Key concepts include ecosystems, populations, communities, and the flow of energy and matter within them. So, UGCNet often delves into ecological theories like the competitive exclusion principle, niche theory, and the study of ecological succession. So, learn those topics in detail. Then, environmental chemistry. This branch focuses on chemical processes in the environment, including pollution, chemical analysis, and toxicology. Topics such as the sources and effects of pollutants, chemical kinetics, and chemical equilibria in natural ecosystems are crucial. Then, geology and earth science. Understanding the earth structure and processes is vital. Topics like plate tectonics, geological timescales, and formation of natural resources like minerals, rocks, fossil fuels are essential. Additionally, geological hazards such as earthquakes and volcanoes are very important. And climatology, climate science explores weather patterns, climate change, and atmospheric processes. Net candidates should be well versed in topics like the greenhouse effect, climate modeling, and the impacts of climate change on ecosystems and society. Then, biodiversity and conservation. Knowledge about biodiversity and its conservation is fundamental. This often include questions related to endangered species, conservation strategies, and the importance of protected areas. Then, environmental policy and management. Environmental governance policies and management strategies are vital for addressing environmental issues. This include understanding international agreements like Kyoto Protocol, Paris Agreement, environmental laws, and sustainable resource management. And environmental ethics and social sciences. Candidates should be familiar with ethical considerations in environmental decision making, environmental justice, the role of society in environmental issues, and the socio-economic impacts of environmental policies are also important. Then, environmental impact assessment or EIA is a critical tool in environment management. What is EIA? Environmental impact assessment. Never forget this. Then, understanding the process of assessing the potential environmental impacts of project policies or developments is crucial. Then, environmental pollution, detailed knowledge of various types of pollution, air, water, soil, noise, and the sources, effects, and control measures is essential. This include understanding pollution monitoring and control technologies. And sustainability, sustainable development principles and practices, including the three pillars of sustainability like economic, social, and environmental, are key components. The knowledge of sustainable resource management, renewable energy sources, and circular economic concepts is beneficial. Research methods, familiarity with research methodologies in environmental science, including experimental design, data analysis, and statistical tools, is necessary. And current environmental issues, stay updated on contemporary environmental challenges such as climate change, biodiversity loss, deforestation, and pollution incidents. These topics are often included. Now we are going to learn about definition, principles, and scope of environmental science. Definition of environmental science. Environmental science is an interdisciplinary field that systematically studies the interaction between humans and the environment and the impact of human activities on the environment. It seeks to understand, analyze, and address environmental issues and challenges to ensure the sustainable coexistence of humanity and the planet. The scientific discipline combines elements from various branches of science, including biology, chemistry, physics, geology, sociology, and economics, to provide a holistic perspective on the environment. Then, principles of environmental science include interconnectedness. The fundamental principle of environmental science is the recognition that everything in the environment is interconnected. Changes in one aspect of the environment can have far reaching consequences. For example, deforestation can lead to soil erosion, loss of biodiversity, and altered weather patterns. Then, sustainability, the principle of sustainability underscores the importance of using natural resources in a manner that does not deplete them for future generations. It advocates for responsible resource management, renewable energy sources, and minimizing waste and pollution. Then, the precautionary principle. Environmental scientists often apply the precautionary principle, which suggests that when there is uncertainty about the potential environment harm of an action or substance, it is better to err on the side of caution and take preventative measures. This principle is crucial in assessing and mitigating environmental risks. Which principle? Precautionary principle. Then conservation. Conservation principles emphasize the preservation of natural resources and biodiversity. This includes the establishment of protected areas, habitat restoration, and sustainable practices to maintain ecosystems' health. Then pollution control. Environmental science acknowledges the need to control and reduce pollution. So principles of pollution control involve identifying pollution sources, then developing technologies to reduce emissions, and enforcing regulations to protect the environment and human health. And environmental ethics. Ethical considerations are integral to environmental science. Principles of ethics guide decision making and behavior, promoting a sense of responsibility and moral duty towards the environment and future generations. Then adaptation and resilience. Given the reality of environmental change, principles of adaptation and resilience are essential. Environmental scientists study ways to help ecosystems and human societies adapt to environmental changes and build resilience against environmental changes and challenges. Scope of environmental science. The scope of environmental science is broad and encompasses various dimensions. First, natural environment. This includes the study of ecosystems, biodiversity, natural resource management, and conservation biology. Environmental scientists assess the health of natural environments, monitoring changes, and develop strategies for preservation. And environmental chemistry. The scope extends to the analysis of pollutants, their sources, and their effects on air, water, soil, and living organisms. So, environmental chemists play a crucial role in identifying and mitigating pollution. Climate and atmospheric sciences. Environmental science involves the study of climate change, meteorology, and atmospheric chemistry. Researchers in this field work to understand climate patterns, assess the impacts of climate change, and develop strategies for mitigation and adaptation. Environmental policy and management. The scope extends to environmental laws, regulations, and policy development. Environmental scientists often collaborate with policymakers to create effective measures for environmental protection. And human impact and social sciences. Understanding the human dimension of environmental issues is critical. This includes studying the social, economic, and cultural factors that influence environmental behavior and decision making. Then technological solutions. Environmental science explores the development and application of technologies for sustainable practices such as renewable energy, waste management, and so eco-friendly agriculture. Then research and education. The field includes research in academia and industry, as well as environmental education and outreach. So researchers in environmental science contribute to scientific knowledge and raise awareness about environmental issues. In conclusion, environmental science is a multidisciplinary field guided by principles of interconnectedness, sustainability, precaution, conservation, pollution control, ethics, adaptation, and resilience. Its scope encompasses the study of the natural environment, pollution control, climate science, policy development, human behavior, technological solutions, and education. Then next, structure and composition of atmosphere, hydrosphere, lithosphere, and biosphere. Atmosphere. The Earth's atmosphere is a complex and dynamic system composed of various layers. Troposphere. The troposphere is the lowest layer and extends from the Earth's surface to approximately 10 to 15 kilometers in altitude. It contains most of Earth's weather systems and is characterized by decreasing temperature with altitude. Then stratosphere. Above the troposphere lies the stratosphere, which extends to about 50 kilometers above the Earth's surface. The stratosphere contains the ozone layer, which plays a crucial role in absorbing harmful ultraviolet UV radiation from the sun. Then mesosphere. Beyond the stratosphere is the mesosphere, extending up to about 85 kilometers. This layer is known for its extremely low temperature and is where meteors burn up upon entering the Earth's surface. Which one? Mesosphere. Meteors, mesosphere. Remember like that. Then thermosphere. The thermosphere is above the mesosphere and has temperatures that increase the altitude increase with altitude due to the absorption of solar radiation. The International Space Station orbits within the thermosphere. Remember that. An exosphere, the outermost layer of atmosphere, is the exosphere where gas molecules gradually transition into outer space. This is here that the atmosphere merges with the vacuum of space. Then composition of the atmosphere. The Earth's atmosphere is primarily composed of gases with the following major components like nitrogen. Nitrogen makes up to approximately 78% of the atmosphere. It is essential for life and is a vital component of proteins and DNA. Then oxygen. Oxygen comprises about 21% of atmosphere. It is essential for respiration in most living organisms. Then argon. Argon is a noble gas that makes up about 0.93% of the atmosphere. It is chemically inert and does not readily react with other elements. Then carbon dioxide, CO2. Wait a minute, first we learned about nitrogen. Then nitrogen makes up approximately 78% of the atmosphere. It is essential for life and is a vital component of proteins and DNA. Then oxygen. Oxygen comprises about 21% of atmosphere. It is essential for respiration in most living organisms. Then argon. Argon is a noble gas that makes up about 0.93% of the atmosphere. It is chemically inert and does not readily react with other elements. Then carbon dioxide. Carbon dioxide is present in trace amounts about 0.04%. This plays a crucial role in the greenhouse effect, regulating Earth's temperature. Then trace gases. The atmosphere also contains trace amounts of other gases including water vapor, variable in concentration, neon, helium, methane and ozone. Then next, hydrosphere. The hydrosphere refers to all the water on Earth, including oceans, rivers, lakes, glaciers, groundwater, and atmospheric water vapor. Then oceans cover about 71% of Earth's surface and contain about 97% of Earth's water. They play a critical role in regulating the planet's climate and are home to a diverse range of marine life. Then freshwater, the remaining 3% of Earth's water is freshwater, with the majority locked in ice caps and glaciers. So accessible freshwater is found in rivers, lakes, and underground aquifers. And water cycle, the hydrosphere is in constant motion through the water cycle, which include processes like evaporation, condensation, precipitation, and runoff. The cycle is essential for maintaining life on Earth. Then lithosphere, the lithosphere refers to the rigid outer layer of the Earth's surface, which include the Earth crust and the uppermost part of the mantle. Then continental crust. The continental crust forms the continents and is composed primarily of granite rocks. It is less dense than the oceanic crust and is rich in various minerals. So we were learning about lithosphere. The lithosphere refers to the rigid outer layer of the Earth's surface, which includes the Earth crust and the uppermost part of the mantle. Then continental crust. The continental crust forms the continents and is composed primarily of granite rocks. It is less dense than the oceanic crust and is rich in various minerals. Then oceanic crust. The oceanic crust underlies the ocean basins and consists mainly of basalt rocks. It is thinner and denser than the continental crust. Then plate tectonics. The lithosphere is divided into tectonic plates that float on the semi-fluid asthenosphere below. Plate tectonics. The movement of these plates tend to geological phenomena like earthquakes, volcanoes, and the creation of mountain ranges. And mineral resources. The lithosphere contains valuable mineral resources such as ores, gold, and precious metals, which are essential for various industries. Then biosphere. The biosphere encompasses all living organisms on Earth and the environment in which they exist. Ecosystems. The biosphere is organized into ecosystems which consist of living organisms, biotic factors, and their physical surroundings. Abiotic factors. Ecosystems can be terrestrial, aquatic, or even aerial. Then biodiversity. The biosphere is rich in biodiversity, with millions of species ranging from microorganisms to plants and animals. Then ecosystems can be terrestrial, aquatic, or even aerial. Then biodiversity. The biosphere is rich in biodiversity with millions of species ranging from microorganisms to plants and animals. Biodiversity is crucial for ecosystem stability and provides numerous ecological services. Then human impact. Human activities such as deforestation, pollution, and habitat destruction have significant impacts on the biosphere. Conservation efforts aim to protect biodiversity and maintain ecological balance. Then food chains and webs. Within the biosphere, organisms are interconnected through food chains and webs, where energy and nutrients flow from one organism to another. So in conclusion, the Earth's environment comprises the atmosphere, hydrosphere, lithosphere, and biosphere, each with its unique structure and composition. Then next, laws of thermodynamics. The laws of thermodynamics is the branch of physics. Thermodynamics is the branch of physics that deals with the principles governing energy, heat, and work interactions in physical systems. It is a fundamental field of study crucial for understanding how energy and matter behave in various natural and engineering processes. The laws of thermodynamics are a set of fundamental principles that govern the behavior of energy and matter in the universe. There are 4 laws of thermodynamics, but the first 2 are the most fundamental and widely applied. First law of thermodynamics, law of conservation of energy. The first law of thermodynamics, also known as the law of conservation of energy, states that energy cannot be created or destroyed in an isolated system. Instead, it can only be, it can only change forms. In other words, the total energy of an isolated system remains constant. Then mathematically, the first law can be expressed as is equal to Q minus W. So Q represents change in internal energy of the system. Q represents heat added to the system. W means the work done by the system on its surroundings. System by the system on its surroundings. Remember that. And this law is fundamental in understanding various energy transformations such as heat engines, chemical reactions, and phase changes. It tells us that energy can be converted from one form to another, but it cannot be lost. Second law of thermodynamics, law of increased entropy. The second law of thermodynamics introduces the concept of entropy and describes the direction of natural process. It states that in any energy exchange, if no energy enters or leaves the system, the potential energy of the state will always be less than that of the initial state. In simpler terms, it asserts that natural processes tend to increase the overall disorder, randomness, or entropy of a system. Mathematically, this can be expressed. Rest represent change in entropy of a system. The law is very often explained through the concept of heat transfer from hot to cold objects, the irreversibility of certain processes, and the tendency for systems to move towards equilibrium. It underlies concepts like the heat engine efficiency limit or Carnot efficiency and the idea that perpetual motion machines are impossible. And third law of thermodynamics, Nernst heat theorem. The third law of thermodynamics, also called the Nernst heat theorem, known as Nernst heat theorem, states that as the temperature of a system approaches absolute zero Kelvin, the entropy of the system approaches a minimum or constant value. What is that? Temperature of a system approaches absolute zero, the entropy of the system approaches a minimum or constant value. In simpler terms, it is impossible to reach absolute zero in a finite number of steps. This law is significant for understanding the behavior of matter at extremely low temperature and is essential in fluids such as cryogenics. Fields such as cryogenics. Then zeroth law of thermodynamics. The zeroth law of thermodynamics establishes the concept of temperature and thermal equilibrium. It states that if two systems are in thermal equilibrium with the third system, they are in thermal equilibrium with each other. This system is fundamental for temperature measurement and the development of temperature scales. What is that? The zeroth law of thermodynamics establishes the concept of temperature and thermal equilibrium. It states that if two systems are in thermal equilibrium with the third system, they are in thermal equilibrium with each other. This law is fundamental for temperature measurement and the development of temperature scales. So we will be having a quick recap about this. First law, the conservation of energy, tells us energy cannot be created or destroyed. The second law, the increase of entropy, defines the direction of natural process. The third law, the unattainability of absolute zero, sets limit on cooling process. Finally, the zeroth law introduces the concept of temperature and thermal equilibrium. These laws have far-reaching implications in physics, chemistry, engineering, and various scientific disciplines. Then next, heat transfer processes. Heat transfer process is a fundamental concept in thermodynamics and plays a critical role in various physical, chemical, and engineering systems. It refers to the exchange of thermal energy between two or more systems due to temperature differences. There are three primary modes of heat transfer: conduction, convection, and radiation. Conduction is the transfer of heat through a solid material without the physical movement of the material itself. It occurs due to the collision of adjacent particles, atoms or molecules within the material. Key points about conduction: Fourier's law. Heat transfer by conduction can be described by Fourier's law, I'm not sure about the pronunciation, which states that the rate of heat transfer through a material is directly proportional to the temperature difference across a material and inversely proportional to its thermal resistance. In thermal conductivity, materials have different thermal conductivities which determine their ability to conduct heat. For example, metals like copper have high thermal conductivity, while insulators like wood have low thermal conductivity. Then applications: conduction is seen in various everyday situations such as cooking on a hot stove, touching a cold object, or heat transfer within a solid structure like a building. And convection is the transfer of heat through a fluid, that means liquid or gas, due to the movement of the fluid itself. This movement occurs because warmer, less dense fluid rises while cooler, denser fluid sinks. Natural convection occurs when the fluid motion is driven by buoyancy forces, often seen in phenomena like the rising of hot air or the circulation of water in a hot pot heated on a stove. Then forced convection involves the use of mechanical devices such as fans or pumps to enhance fluid movement, increasing heat transfer rates. One example includes forced air heating systems and cooling fans in electronics. Convection is vital in natural processes like weather patterns and ocean currents, and is extensively used in engineering for heat exchangers, cooling systems, and HVAC. That means heating, ventilation, and air conditioning. Then radiation. Radiation is the transfer of heat in the form of electromagnetic waves or infrared radiation that do not require a medium, unlike conduction and convection. All objects emit and absorb thermal radiation. Stefan Boltzmann law. This law describes the total power radiated per unit surface area of an ideal black body. It states that the power radiated is directly proportional to the fourth power of the body's absolute temperature. What is that? Power radiated is directly proportional to the fourth power of the absolute body's temperature. Then emissivity. Real objects have emissivity values less than 1, representing their ability to emit and absorb radiation. Emissivity varies with material and surface properties. So, radiation plays a crucial role in the Earth's energy balance, including solar radiation from the sun and the re-radiation of heat by the Earth's surface. It is also significant in various technologies such as infrared thermography, solar panels, and microwave ovens. Then, combined heat transfer. In many real-world situations, multiple modes of heat transfer can occur simultaneously. This is known as combined heat transfer. For example, heating a pot of water on a stove involves conduction through the pot's material, convection within the water, and radiation between the pot and its surroundings. Then, understanding heat transfer processes is essential in fields like thermodynamics, material science, engineering, and environmental science. It allows scientists and engineers to design efficient heating and cooling systems, predict climate patterns, and develop innovative technologies for energy conversion and thermal management. Then, mass and energy transfer across various interfaces. Mass and energy transfer across interfaces. Mass and energy transfer across interfaces is a fundamental concept. So, it involves the movement of matter and energy between different regions or phases such as solids, liquids, gases, and plasma. Understanding this process is crucial for the wide range of applications, from chemical reactions and heat transfer to environmental phenomena and material science. Mass transfer across interfaces. Mass transfer is the movement of substances from one region to another, driven by differences in concentration. It commonly occurs across interfaces like gas, liquid, or solid liquid boundaries. There are several mechanisms of mass transfer. First, diffusion. This is the most common mechanism of mass transfer and occurs due to the random motion of molecules. It involves the net movement of molecules from regions of high concentration to regions of low concentration. The Fick's law of diffusion describes the rate of diffusion, which depends on the concentration gradient and the diffusion coefficient. Then, convection. In addition to diffusion, mass transfer can occur through convection. Convection involves the bulk movement of fluids which carries substances with them, and it is driven by differences in pressure, density or temperature. Then mass transfer coefficients. Mass transfer across interfaces is often characterized by mass transfer coefficients which describe the efficiency of the transfer. These coefficients depend on properties of system and the specific interface. Applications. Mass transfer is essential in chemical engineering process such as distillation, absorption and filtration, as well as in biological process like osmosis and gas exchange and respiration. Then energy transfer across interfaces. Energy transfer across interfaces is primarily associated with heat transfer, which involves the movement of thermal energy from regions of higher temperature to regions of lower temperature. There are three main modes of heat transfer. First, conduction. Conduction is the transfer of heat through a solid material without the movement of the material itself. It occurs due to collision of adjacent particles within the material. The rate of heat conduction is described by Furner's law we just mentioned. Then convection. Convection, as mentioned earlier, involves the movement of fluids, liquids or gases, and the transfer of heat by the movement of the fluid itself. It can be natural, like buoyancy driven, or forced, mechanically driven. Then radiation. Radiation is the transfer of heat in the form of electromagnetic waves, infrared radiation that do not require a medium. Then all objects emit and absorb thermal radiation. The Stefan-Boltzmann law describes the total power radiated by an ideal black body. Heat transfer is critical in everyday situations like cooking, heating and cooling buildings and electronic devices. It is also essential in engineering applications such as heat exchangers, refrigeration systems and thermodynamics. An interface in environmental science. In environmental science, mass and energy transfer across interfaces play a crucial role. For example, in atmosphere, energy transfer occurs through radiation from the sun and the re-radiation of heat by the Earth's surface. In aquatic ecosystems, mass transfer involves the movement of nutrients and gases between water and sediments. Then in soil science, the transport of water and solutes across soil interface is vital for plant growth and groundwater recharge. So understanding this process is essential for addressing environmental challenges, predicting climate patterns, and managing natural resources. In conclusion, mass and energy transfer across interfaces are fundamental concepts in science and engineering. This process plays a vital role in various fields and applications ranging from chemical reactions and heat transfer to environmental phenomena and material science. Then material balance. Material balance, also known as mass balance or mass conservation, is a fundamental concept in engineering, environmental science, and chemistry. It involves accounting for the flow and transformation of substances or matter within a closed system. Material balance equations are used to describe the conservation of mass during physical or chemical processes. Understanding material balance is crucial for various applications, including chemical engineering, environmental engineering, and process optimization. Then, key concepts in material balance. Conservation of mass. The fundamental principle of material balance is the conservation of mass, which states that the total mass of a closed system remains constant over time, regardless of the processes occurring within it. In other words, mass cannot be created or destroyed, it can only change forms. Then, closed systems. Material balance calculations typically apply to closed systems where no mass is exchanged with the surroundings. This assumption simplifies calculations and is often suitable for many engineering and scientific applications. First point is that total mass of a closed system remains constant over time regardless of the processes occurring within it. Components in material balance calculations. Substances are divided into components or species based on their chemical nature. These components are tracked individually throughout a process. Then material inflow and outflow. Material balance equations account for material inflow, that means inflow inputs and outflow outputs into and from the system. This includes feed streams, product streams, and any other source or sinks of material. Then reactions and transformations. In addition to physical transport, material balance can include chemical reactions and transformations. For example, in a chemical reactor, reactants are transformed into products, and materials balance ensures that the total mass remains conserved. Then material balance equations are derived based on the principles mentioned above. Accumulation represents the change in the mass of a particular component within the system over a specified time interval. It accounts for any net increase or decrease in mass due to processes occurring within the system. So inflows include all the sources of the component entering the system, such as feed streams, additions or inputs into other processes. Outflows encompasses all the streams carrying component out of the system, including product streams, removals or transfers to other processes. Then generation and consumption, the streams account for the creation of or destruction of component within the system, typically due to chemical reactions or other transformations. Then next we will be learning tomorrow.